L'Hopital's rule when you're trying to find the limits for rational functions. Okay, so if we have a function like f of x over g of x, and we're trying to find the limit as x approaches a, if that limit looks like 0 over 0 when you put in the a, so if f of a is 0 and g of a is 0, okay, or if the limit as x approaches a of f of x over g of x looks like we're going to get infinity over infinity, whether it's plus or minus infinity. Okay? Then we have what's called an indeterminate form. And this is called these are two different forms. So we have a limit of indeterminate form. Zero over 0. And this one, obviously, is determinate form infinity over infinity. Okay? Now we have used techniques to solve these limits without using L'Hopital's rule. Sometimes we can do it and sometimes we can't do it. Okay? But L'Hopital's rule will allow us to determine all of them. Okay? So, this is how it works. L'Hopital's rule says if f and g are differentiable, okay, and the derivative of g, the denominator is not 0, except having it be 0 in a location is okay. As long as g of x, g prime of x, the first derivative is not 0 everywhere. It can be 0 at a, and we'll see how we will deal with that. We'll do some examples like that, okay? And if the limit as x approaches a of f of x equals the limit as x approaches a of g of x, and that equals 0 or infinity or negative infinity, okay? So it's just what we were saying up above. That limit is going to be 0 over 0 or infinity over infinity or negative infinity over negative infinity for the rational function. Then, and here's the nice part, to find the limit of f of x over g of x as x approaches a, we can find the limit of f prime of x over g prime of x. So we can take the derivatives and find the limits. And why that's nicer is because sometimes the derivative is a less complex function, but also because sometimes then we can simplify this. And so instead of getting 0 over 0, it'll simplify and not give us 0 over 0, and we can actually find the limit. Because what it's saying is that the function at a is pretty close to the derivative of the function at a, because this is the slope of the tangent, right? So the slope of the tangent at a is pretty close to the value of the function at a. So it's just using that same approximation that we've been using when we did linear approximations the other day when some of you guys were at Playland. Because we're basically just zooming in on the function at a. And when we zoom into the function at a, the tangent and the function itself are almost indistinguishable at that point. So that's what we're saying, okay? So it's using a ratio of linear functions or a ratio of slopes, which is usually nicer. So we'll do some examples. They can get tricky. One of the important things to watch out for, though, before you use L'Hopital's rule, is to make sure that you have this going on, that you do have 0 over 0. If you don't have 0 over 0, you don't use L'Hopital's rule. You solve this the way you would normally solve it, or if you have infinity over infinity. I don't want this to be shown again, so let's do that. Okay? Questions so far? All right, so let's do some examples. Okay, so the limit as x approaches 1 of ln x over x minus 1. This doesn't simplify in here, okay? And if we put 1 in here, what's the ln of 1? 0, and 1 minus 1 is 0. So this limit goes to 0 over 0. So this is a perfect situation for L'Hopital's rule. So because we get 0 over 0, what we want to do is take the derivative of the top, the derivative of the bottom, and then take that limit as x approaches 1 and see what is going to happen there. So what's the derivative of ln x? 1 over x. And the derivative of x minus 1 is 1. So we get 1 over x. And when that goes to 1, we get 1. So that limit is actually 1. Okay? See how that works? All right, let's try this one. The limit as x goes to infinity of e to the x over x squared. Okay? So if we have e to the infinity, that's infinite. And if we have infinity squared, that's infinite as well. So this is an indeterminate form of infinite over infinite, right? So what we want to do is take the derivative of the top and the bottom. So what is the derivative of e to the x?
E to the x.
E to the x. And the derivative of x squared?
2x.
Is 2x. Okay? But again, we have infinity over infinity. So what can we do? Do it again. Derivative of e to the x is e to the x. Derivative of 2x is 2. So now we don't have an indeterminate form anymore. We have infinity over 2. But infinity over 2, now we can be assured that it is infinity. Okay? But if the top and the bottom are both infinite, we don't know what's going on. We need to keep testing that. Okay? Just like here, the top and the bottom were both 0. Sorry, here the top and the bottom were both 0, so we needed to keep testing it because, in this case, 0 over 0 actually is 1. Okay? Okay? Here we have the limit as x approaches infinity of ln x over the cube root of x. What's the ln of infinity? Any ideas? It's infinity. And the cube root of infinity? Also infinity. So this is an indeterminate form of infinity over infinity. So the derivative of ln x, the derivative of the cube root of x, whoops, minus 2/3, right? Okay, so it looks like that. So now we want to simplify that up a little bit and see what that actually looks like. I'm going to multiply top and bottom by x. Well, actually, I'm not even going to do that. I'm going to bump the x down below. The 3 comes up, and that comes up here. So I get 3x to the power of 2/3 over x. Okay? And you can do the algebra if you want. But this x, because this is 1 over x, that x goes down below. Because this is x to the power of a negative, that goes up top. And 1 over 3, the 3 goes up top. So we get that. And that simplifies. Because what do I do when I'm dividing powers with the same base? I subtract the exponents. And so 2/3 take away 1. Am I doing this right? Is negative 1/3. So I get x to the negative 1/3, which is, I'm tired of going horizontally here. I'm going to go vertically. I probably should have done that right from the beginning. The limit is x goes to infinity. So this is 3 over the cube root of x. So what's that derivative? Or what's that limit?
0.
0, because it's 3 over infinity. Anything over infinity is 0. Okay? So this one looked like infinity over infinity. That was the indeterminate form, but the limit is actually 0, because the bottom goes to infinity faster than the top in the end. Okay? Questions so far? The hardest ones are the trig. Okay, so I'll do one trig one with you before I turn you loose to do some practice. The limit of tan x minus x over x cubed as x goes to 0. What's the tan of 0? 0. So I have 0 minus 0 on top. 0 cubed, I have 0 on the bottom, so this is an indeterminate form of 0 over 0. Always check that, because if it's not an indeterminate form, then you don't want to use L'Hopital's rule. All right, we need to take the derivative. What's the derivative of tan x? Okay. So now, at this point, you have some choices. Secant squared x, you could recognize that as a Pythagorean identity. It's tan squared x. Okay? Or you can just take the derivative again, because this is 0. And what's secant squared x? Pardon me? It's secant 0 is minus 1 squared is 1. So it's 1 minus 1. Okay? Secant is opposite of cos. No, secant 0 is 1. Okay? So we got 1 minus 1. So we have 0 over 0. So, what do you want to do? Identity or derivative? How are you doing, Curtis?
Identity.
Okay, identity. So secant, so this is tan squared x over 3x squared. Still 0 over 0. So now we have to take the derivative of that. What's the derivative of tan squared x? Got to use the?
2 tan x and then secant squared x.
Yeah, use the chain rule there. All over 6x. Okay? How are we doing so far? Still 0 over 0. However, let's go. Let's take,
Cancel out.
yeah, the 2 and the 6 will divide out, so we get a 3. Okay? So what I'm going to do at this point is remember that the rule for limits, here I have a product, so I can do the limit as x approaches 0 of tan x over x times 1/3 of the limit as x approaches 0 of secant squared x. Okay, so I'm just taking each derivative individually, and this 1/3, because it's a constant, I'm just pulling it outside. I can put it out here too. Now what's the limit as x approaches 0 of secant squared x? 1. So I have 1/3 times that. 1/3 times the limit as x approaches 0 of tan x over x. Okay, what are we going to do here?
Derivative
Derivative one last time.
1 over
Derivative of tan x, secant squared x over 1, and secant of 0 is 1, so I get 1/3. Okay? So the trig ones are trickier sometimes because you have to either use identities or keep taking the derivative. Now, just as an aside, if I had not used identities here, if I had taken the derivative, I still would have got to there, so it wouldn't matter. Okay? So it's your choice, really, at that point. Sometimes using an identity can make it easier to get there, though. Okay, so you are going to practice today, second edition. Starts on page 212. Third edition, pages 240 to 241. I think it's the last topic in the second edition, but there's more in the third edition, but I could be wrong there. Anyways, have a look at those. Think about them. Good practice with your derivatives. Yeah. Oh, somebody's eraser. Is this yours, Audrey? Eraser? Did anybody lose an eraser? Okay. Oh, let me stop the recording.